Tonight, we're diving into something that sounds deceptively simple, but might be the most confusing idea in all of physics. Space-time. You've heard the word thrown around constantly. Einstein's theory of space-time. But here's what almost nobody realizes. When you actually try to understand what space-time is, when you dig past the surface explanations and ask what it's really made of, you hit a wall. We don't know. We can measure space-time. We use it to make your phone's GPS work. We've watched it bend around black holes and vibrate in gravitational waves. And yet, we don't know what it's fundamentally made of, or even whether "made of" is the right question. Space-time works, but we don't truly understand it. By the end of tonight, you're going to understand why space-time remains one of the biggest unsolved mysteries in physics, why the smartest people on Earth are still arguing about it, and why solving this mystery might change everything we think we know about reality itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start in 1905. Albert Einstein was 26 years old, working as a patent clerk in Bern, Switzerland. He wasn't a professor. He didn't have a position at any university. He spent his days examining patent applications for electromagnetic devices, and he spent his nights thinking about physics. In that single year, 1905, he published 4 papers that would completely revolutionize physics. One paper explained Brownian motion and proved that atoms were real, physical objects, not just theoretical constructs. One paper explained the photoelectric effect and helped establish the foundations of quantum mechanics. And 2 papers introduced what we now call special relativity. Special relativity sounds impossibly complicated, but the core idea is actually straightforward. Einstein realized that the speed of light is always the same, no matter how fast you're moving. This seems impossible at first. If you're on a train moving at 62 miles per hour and you throw a ball forward at 12 miles per hour, someone standing on the platform sees the ball moving at 74 miles per hour. The speeds add up. That's common sense. That's what we expect from everyday experience. But Einstein showed that light doesn't work this way. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, you might think the light would move at 1.5 times the speed of light from the perspective of someone watching you. But it doesn't. The light moves at exactly the speed of light, about 186,000 miles per second, both from your perspective inside the ship and from the perspective of someone watching from outside. The same speed, always. This seems completely impossible. How can light be moving at the same speed for both observers when one observer is already moving at half the speed of light? Einstein's answer was radical, revolutionary, and initially very hard to accept. Space and time adjust themselves to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the perspective of someone standing still. And distances in the direction you're moving actually contract. They physically shrink. These aren't optical illusions or measurement errors. They're real physical effects built into the structure of reality. Time and space are not absolute, unchanging backgrounds where events happen. They're relative, flexible, depending on your motion through the universe. The only thing that's absolute, that's the same for everyone, regardless of how they're moving, is the speed of light. This was shocking in 1905. It overturned centuries of assumptions about how the universe works. Isaac Newton had built classical physics on the idea that time flows at the same rate for everyone, that a second is a second, no matter where you are or how fast you're moving. That space is a fixed stage where events play out. Einstein showed that wasn't true. Time is flexible. Space is flexible. They bend and stretch depending on your motion. Think about what this really means. If you could build a spaceship that travels at 99% of the speed of light, and you took a journey to a star 10 light-years away and back, from your perspective on the ship, the journey might only take a couple of years. You'd experience a few years of time passing. You'd age a few years. But when you return to Earth, 20 years would have passed. Your friends would be 20 years older. Your children might now be older than you. This isn't science fiction. This is what Einstein's equations predict, and it's been confirmed by experiments countless times. We've tested this with particles in accelerators. Unstable particles that normally decay in microseconds live much longer when they're traveling at 99.9% of light speed. Their internal clocks run slower from our perspective. We've tested it with atomic clocks on airplanes. When you fly an atomic clock around the world and compare it to an identical clock that stayed on the ground, the traveling clock shows less time has passed. The difference is tiny, just a few hundred nanoseconds, but it's measurable and real, and it matches Einstein's predictions exactly. The implications are profound and unsettling. There's no universal now. No cosmic clock ticking at the same rate everywhere in the universe. When you say something is happening right now on a distant planet, that statement has no absolute meaning. Different observers moving at different speeds would disagree about what right now means. They would disagree about which events are simultaneous, which events happen at the same time. Time is not a river flowing at a constant rate for everyone. It's more like a fabric that can stretch and compress depending on how you're moving through it. But Einstein wasn't done. Special relativity only dealt with objects moving at constant speeds. It didn't handle acceleration. It didn't handle gravity. And gravity was a major problem. Newton's law of gravity had worked brilliantly for over 200 years. You could use it to predict the motion of planets with incredible accuracy. You could calculate the trajectory of cannonballs. You could predict the orbits of moons around their planets. It was one of the great triumphs of classical physics. But Newton's gravity had a problem that became obvious once Einstein developed special relativity. Newton said that gravity acts instantaneously across any distance. If the sun suddenly disappeared, Earth would immediately feel the change in gravity and fly off into space. But special relativity said nothing can travel faster than light. Information can't propagate instantaneously. If the sun disappeared, Earth shouldn't know about it until at least 8 minutes later, the time it takes light to travel from the sun to Earth. This was a fundamental conflict. Newton's gravity and Einstein's relativity couldn't both be right. One of them had to give way. Einstein spent years thinking about this problem. He struggled with it, made false starts, published preliminary ideas that turned out to be wrong. The breakthrough came in 1907 when he had what he later called the happiest thought of his life. Imagine you're standing on the ground. You feel your weight, the force of gravity pulling you down toward Earth's center. Now, imagine someone in a windowless room in space, far from any planets or stars. If their room is sitting still, in empty space, they'd float weightlessly. But if their room is accelerating upward, if a rocket engine is pushing it faster and faster, they'd feel a force pushing them toward the floor. They'd feel weight, exactly like they feel weight on Earth. Einstein realized something remarkable. Being in an accelerating room far from any gravity is indistinguishable from standing still in a gravitational field. You can't tell the difference. There's no experiment you can do inside that room to determine whether you're on Earth's surface, experiencing gravity, or in a rocket in deep space, accelerating upward. The effects are identical. Now, imagine the opposite situation. Imagine you're in an elevator and the cable breaks. You're in free fall, accelerating downward. During those terrifying seconds before you hit the ground, you'd feel weightless. If you let go of your phone, it wouldn't fall to the floor of the elevator. It would float next to you because you're both falling at the same rate. This is exactly what astronauts on the International Space Station experience. They're not beyond Earth's gravity. They're still well within it, only about 250 miles up. They feel weightless, not because there's no gravity, but because they're in continuous freefall. They're falling toward Earth, but they're also moving sideways fast enough that they keep missing Earth. They're in orbit, continuously falling, but continuously missing the ground. Einstein realized that being in freefall is indistinguishable from being in empty space with no gravity at all. And being in a rocket accelerating upward is indistinguishable from standing on the surface of a planet feeling gravity pull you down. You can't tell the difference. If you're in a closed room with no windows, there's no experiment you can do to determine whether you're sitting on Earth's surface, feeling 1g of gravity, or sitting in a rocket in deep space, accelerating upward at 1g. The effects are identical. This is called the equivalence principle. Acceleration and gravity are equivalent. They're the same thing, just viewed from different perspectives. And this was the key insight that led Einstein to his theory of general relativity. If acceleration and gravity are the same thing, and if special relativity says that acceleration affects space and time, then gravity must also affect space and time. Gravity must curve space and time. It took Einstein another 8 years to work out the mathematics. From 1907 to 1915, he struggled with the equations. He learned advanced mathematics he'd never studied before. He made mistakes, published wrong results, corrected them, and tried again. It was the hardest intellectual work of his life. He later said, the final year, from late 1914 to November 1915, was the most exhausting and demanding time of his entire career. But in November 1915, he finally got the equations right. He published his theory of general relativity, and physics would never be the same. General relativity says that mass and energy curve spacetime, and objects moving through curved spacetime follow curved paths. That's what we experience as gravity. It's not a force pulling objects together across empty space. It's objects following the straightest possible paths through warped geometry. Those paths just happen to curve because the geometry itself is curved. The classic analogy is a rubber sheet. Imagine stretching a flat rubber sheet taut. If you place a heavy ball in the middle, it creates a dip, a curve in the sheet. Now, if you roll a smaller ball across the sheet, it will curve toward the heavy ball. Not because the heavy ball is pulling it with some invisible force, but because the sheet itself is curved. The small ball is trying to roll in a straight line, but the curved sheet forces it to follow a curved path. This is what mass does to spacetime. The sun, with its enormous mass, curves spacetime around it. Earth is trying to move in a straight line through space. But the curved spacetime around the sun forces Earth to follow a curved path. That curved path is Earth's orbit. We experience this as the sun's gravity pulling on Earth. But from Einstein's perspective, There's no pull at all. There's just Earth moving through curved space-time. Now, this rubber sheet analogy is helpful, but it's also misleading in important ways. The rubber sheet is a two-dimensional surface curving in three-dimensional space. But space-time is four-dimensional, 3 dimensions of space plus 1 of time, and it's not curving in some higher dimensional space. It's curving in on itself. This is genuinely hard to visualize because we can't picture four-dimensional geometry. Our brains evolved to understand 3 spatial dimensions, not 4-dimensional space-time. Also, the rubber sheet analogy makes it look like gravity is pulling the balls down, but that's our Earth's gravity doing the pulling in the analogy. In real space-time, there's no external force. The curvature itself is gravity. Objects follow what are called geodesics, which are the straightest possible paths through curved space-time. A planet orbiting a star is following a geodesic. It's moving in what it perceives as a straight line through space-time. But because space-time is curved, that straight line curves back on itself, creating an orbit. Einstein struggled for years to find the right mathematical language to express these ideas. He needed tensor calculus, a branch of mathematics that deals with objects that have multiple indices and transform in specific ways when you change coordinate systems. He'd never studied this in detail during his university education. He had to learn it from his mathematician friend, Marcel Grossman. Together, they worked through the mathematics, trying different formulations, making mistakes, publishing preliminary versions that turned out to be wrong. At one point, Einstein thought he had the right equations, published them, then realized they didn't reduce to Newton's law of gravity in the appropriate limit. That should have been a red flag. Any new theory of gravity has to match Newton's predictions when gravitational fields are weak and objects are moving slowly, because Newton's theory works perfectly well in those situations. Einstein's preliminary equations didn't do this, so he went back to the drawing board. The breakthrough came in November 1915. Einstein was in Berlin, working feverishly on the equations. He gave a series of lectures at the Prussian Academy of Sciences, presenting his progress week by week as he refined the theory. On November 25, 1915, he presented the final form of the field equations. These are now called Einstein's field equations, and they're among the most important equations in all of physics. They look deceptively simple when written in modern notation, but they're actually a set of 10 coupled, non-linear, partial differential equations. They're incredibly difficult to solve. Even today, with powerful computers, we can only solve them exactly for very simple, highly symmetric situations. For more realistic scenarios, we have to use approximations or numerical simulations. But despite their complexity, Einstein's equations make clear predictions, and those predictions have been tested over and over again for more than a century. Every single test has confirmed the theory. The first major test came almost immediately. Remember that problem with Mercury's orbit that Newton's theory couldn't explain? Mercury orbits the Sun in an ellipse, and that ellipse slowly rotates over time, a phenomenon called precession. Newton's equations predicted how much Mercury should precess based on the gravitational influence of the other planets. But observations showed Mercury was precessing about 43 arc-seconds per century more than predicted. That's about 1/18th of a degree per century. Incredibly small, but real and measurable. Scientists had searched for explanations for decades. Maybe there was an undiscovered planet called Vulcan, orbiting between Mercury and the Sun, pulling on Mercury with its gravity. Astronomers searched for Vulcan for years. It didn't exist. Maybe Newton's laws needed some small adjustment. Nothing worked. When Einstein applied his new equations to Mercury's orbit, they predicted exactly the right amount of precession. 43 arc-seconds per century, matching the observations perfectly. Einstein later said that when he realized this, his heart pounded so hard he was afraid he might have a heart attack. It was confirmation that his theory was right. The next major test came in 1919. Einstein's theory predicted that light should bend when it passes near a massive object. This was revolutionary. Newton's theory said light always travels in straight lines. But Einstein said light follows geodesics through curved spacetime, and near a massive object like the Sun, those geodesics are curved. During a total solar eclipse in 1919, the British astronomer Arthur Eddington led expeditions to observe stars near the Sun's edge. Normally, you can't see stars near the Sun because the Sun is so bright. But during a total eclipse, when the Moon blocks the Sun's light, you can see stars in the sky right next to where the Sun appears. Eddington measured the positions of these stars and compared them to their normal positions. When the Sun wasn't nearby, the stars appeared shifted, exactly as Einstein predicted. Their light had been bent by the Sun's gravity as it passed near the Sun on its way to Earth. The deflection was tiny, about 1.75 arc-seconds, about 1/2000th of a degree. But it was measurable, and it matched Einstein's prediction. When the results were announced, Einstein became world famous overnight. Newspapers around the world ran headlines about how a German scientist had overthrown Newton and revolutionized our understanding of the universe. Einstein went from being an obscure physics professor to being a household name. Since then, we've tested general relativity in countless ways, and it's passed every single test. We've measured the bending of light around massive galaxies, a phenomenon called gravitational lensing. We've detected the slowing of time in strong gravitational fields. We've observed the orbits of binary pulsars, pairs of neutron stars orbiting each other, and watched them slowly spiral inward as they lose energy to gravitational waves, exactly as Einstein's equations predict. Let me tell you about one of the most remarkable tests. In the 1970s, astronomers discovered a binary pulsar system called PSRB 1913 plus 16. A pulsar is a rapidly rotating neutron star that emits beams of radio waves like a lighthouse. This particular system consists of two neutron stars orbiting each other. One of them is a pulsar, so we can track its motion with incredible precision by timing the pulses we receive. The pulses arrive with clockwork regularity, like a cosmic metronome. But the timing changes slightly as the pulsar orbits its companion. When it's moving toward us, the pulses arrive slightly earlier. When it's moving away, they arrive slightly later. By carefully analyzing these timing variations, astronomers could determine the masses of both neutron stars, the size of their orbit, how elliptical it is, and how the orbit is changing over time. General relativity predicts that this system should be losing energy by emitting gravitational waves. As it loses energy, the orbit should shrink. The neutron stars should spiral closer together. The orbital period should decrease. The effect is tiny. The orbital period was about 8 hours. General relativity predicted it should decrease by about 76 microseconds per year. That's 76 millionths of a second per year. But pulsars are such precise clocks that this could be measured. And over decades of observations, astronomers found that the orbital period was decreasing at exactly the rate Einstein's equations predicted. Exactly. This was the first indirect evidence for gravitational waves. It showed that gravitational waves must exist and must carry away energy from the system. It was powerful confirmation of general relativity. Russell Hulse and Joseph Taylor, who discovered this system and made these measurements, won the Nobel Prize in Physics in 1993. But that was just indirect evidence. The Holy Grail was to directly detect gravitational waves passing through Earth. This is incredibly difficult. A gravitational wave from even a catastrophic event like two black holes colliding stretches and squeezes space by an almost unimaginably tiny amount. When the waves from that first detection in 2015 passed through the LIGO detectors, they changed the length of the 2.5-mile arms by about 1/10,000th the diameter of a proton. To put that in perspective, imagine trying to measure the distance to the nearest star, about 4 light-years away, to an accuracy of about the width of a human hair. That's the level of precision needed. The LIGO detectors use laser interferometry. They split a laser beam and send it down 2 perpendicular arms, each 2.5 miles long. The beams bounce off mirrors at the ends of the arms and come back to the detector where they're recombined. If both arms are exactly the same length, the 2 beams are in phase when they recombine and they interfere constructively. But if one arm is even slightly longer than the other, the beams are out of phase and they interfere destructively. When a gravitational wave passes through, it stretches one arm while squeezing the other. Then it does the opposite, squeezing the first arm while stretching the second. This oscillating change in length causes the interference pattern to oscillate. The challenge is that everything else also causes the arms to change length. Seismic vibrations from earthquakes, traffic, ocean waves. Thermal fluctuations causing the metal of the detector to expand and contract. Quantum fluctuations in the laser light itself. Even cosmic rays hitting the mirrors. All of these noise sources had to be reduced or compensated for. The detectors are isolated from seismic vibrations by elaborate suspension systems. The laser systems are stabilized to incredible precision. The entire apparatus is kept in an ultra-high vacuum to eliminate air currents. Even with all these precautions, detecting gravitational waves required decades of engineering development. The first large-scale detectors were built in the 1990s and early 2000s. They ran for years without detecting anything. The signals were just too weak, buried in the noise. But the detectors were upgraded, made more sensitive. And on September 14, 2015, at 5:51 a.m. Eastern Time, both LIGO detectors, one in Louisiana and one in Washington State, picked up a signal, a distinctive chirp. Starting at low frequency and sweeping up to higher frequency over about 1/5 of a second. This was the signature of 2 black holes, each about 30 times the mass of the Sun, spiraling into each other and merging. They were about 1.3 billion light-years away. As they spiraled closer, they orbited faster. The gravitational waves they emitted increased in frequency and amplitude. Finally, they merged, creating a single black hole of about 62 solar masses. About 3 solar masses worth of energy was converted directly into gravitational waves in the final moments before merger. For that brief instant, this collision released more power than all the stars in the observable universe combined. The signal matched the predictions of general relativity perfectly. The frequency, the amplitude, the rate of change, everything. This was announced in February 2016. It was one of the most important scientific discoveries of the century. It opened an entirely new way of observing the universe. Since then, we've detected dozens of these events. Black hole mergers, with masses ranging from about 8 solar masses to over 100. Neutron star mergers. Even hints of exotic objects that might be neither black holes nor neutron stars. Each detection tests general relativity in extreme conditions. And each time, the theory passes. We've also seen the first image of a black hole. In April 2019, the Event Horizon Telescope collaboration released an image of the supermassive black hole at the center of the galaxy Messier 87. This wasn't a photograph in the traditional sense. It was created by combining data from 8 radio telescopes spread around the world. Together, they formed a virtual telescope the size of Earth. The image shows a dark circle surrounded by a bright ring. The dark circle is the black hole's shadow. This is the region where space-time is so warped that light cannot escape. Any light emitted from within this boundary is trapped, falling into the black hole. The bright ring is light from hot gas swirling around the black hole just outside the event horizon. Some of this light is bent around the black hole by its intense gravity before reaching us. The size of the shadow depends on the mass of the black hole and on the predictions of general relativity. If general relativity is wrong, the shadow would be a different size or a different shape. But the observed shadow matches general relativity's predictions exactly. The black hole has a mass of about 6.5 billion times the mass of the Sun. The shadow has exactly the size and shape Einstein's equations predict. Every one of these observations confirms the theory. Space-time is real. It can be curved by mass and energy. It can ripple. It can be measured and photographed. And in 2015, exactly 100 years after Einstein published his theory, we directly detected gravitational waves for the first time. Gravitational waves are ripples in space-time itself. When massive objects accelerate, like 2 black holes orbiting each other and eventually colliding, they create waves that spread out through space-time at the speed of light. These waves stretch and squeeze space as they pass by. The effect is incredibly tiny. The gravitational waves detected in 2015 came from 2 black holes, each about 30 times the mass of the Sun, colliding about 1.3 billion light-years away. When those waves reached Earth, they stretched and squeezed space by about 1/10,000th the diameter of a proton. That's an incomprehensibly small amount. But the LIGO detectors were sensitive enough to measure it. LIGO uses laser interferometry. It shoots laser beams down 2 arms, each 2.5 miles long, and measures the time it takes for the light to bounce back. When a gravitational wave passes through, one arm gets slightly longer while the other gets slightly shorter, changing the time it takes for light to travel down each arm. The difference is minuscule but detectable. Since that first detection, we've detected dozens of gravitational wave events, colliding black holes, colliding neutron stars, events producing more energy in a few seconds than all the stars in the observable universe combined. We're now doing astronomy with gravitational waves, observing the universe in an entirely new way. And in 2019, we saw the first image of a black hole. The Event Horizon Telescope, a worldwide network of radio telescopes working together, captured an image of the supermassive black hole at the center of the galaxy M87. The image shows a dark circle surrounded by a bright ring of glowing material. The dark circle is the black hole's shadow, the region of spacetime so curved that not even light can escape. Every one of these observations confirms Einstein's theory. Spacetime is real. It can be curved by mass and energy. It can ripple. It can be measured and photographed. But here's the thing. We still don't know what it actually is. Let me explain what I mean by that. Einstein's general relativity describes how spacetime behaves. It tells us that mass curves spacetime. It tells us that objects follow geodesics through curved spacetime. It gives us equations we can use to calculate those curves and predict the motion of objects. But it doesn't tell us what spacetime is made of. It treats spacetime as a smooth, continuous fabric. You can zoom in on it as much as you want, and it's still smooth. There's no smallest unit, no fundamental building block. It's infinitely divisible. But we know from quantum mechanics that this can't be the whole story. Quantum mechanics says that everything in nature comes in discrete units at small enough scales. Energy comes in packets, called quanta. That's where the word quantum comes from. Light comes in packets called photons. Matter is made of atoms, which are made of protons, neutrons, and electrons. Those protons and neutrons are made of quarks. Everything we've studied in detail turns out to be quantized at small enough scales. So it seems reasonable to think that spacetime itself must also be quantized. There must be some smallest unit of space and time, some fundamental building block that spacetime is made of. This is where quantum gravity comes in. Quantum gravity is the attempt to combine Einstein's general relativity with quantum mechanics. To develop a theory that describes how spacetime behaves at the smallest scales, where quantum effects become important. And this is where we run into serious problems. General relativity and quantum mechanics are both incredibly successful theories. They've been tested extensively, and they work beautifully within their domains. But they don't fit together. They're based on fundamentally different assumptions about how the universe works. General relativity treats spacetime as smooth and continuous. Quantum mechanics says things are discrete and uncertain. General relativity is deterministic. If you know the state of the universe now, you can calculate its state at any other time. Quantum mechanics is probabilistic. You can only calculate the probability of different outcomes. These are fundamentally different worldviews, and they clash when you try to apply both to the same situation. Like the interior of a black hole, or the Big Bang, or any situation involving very strong gravity and very small distances. Let's talk about what happens when you try to combine them. One of the first things physicists tried was to treat gravity like the other forces. The electromagnetic force is carried by particles called photons. The weak nuclear force is carried by particles called W and Z bosons. The strong nuclear force is carried by particles called gluons. So maybe gravity is also carried by particles. These hypothetical particles are called gravitons. If you try to build a quantum theory of gravity using gravitons, you run into problems immediately. The calculations produce infinities. When you try to calculate the probability of certain events happening, the answer comes out as infinity, which is clearly wrong. Probabilities can't be infinite. They have to be numbers between 0 and 1. Physicists have developed techniques for dealing with infinities in quantum field theory. These techniques, called renormalization, work beautifully for the electromagnetic force and the weak and strong nuclear forces. But they don't work for gravity. The infinities in quantum gravity are uncontrollable. They don't go away, no matter what tricks you try. This suggests that treating gravity as just another force carried by gravitons doesn't work. Gravity is different. It's not just a force acting in space-time. It is space-time. So, physicists have tried more radical approaches. Maybe space-time itself is quantized. Maybe space comes in smallest possible units and time comes in smallest possible moments. Maybe, if you zoom in far enough, space-time isn't smooth at all. Maybe it's grainy, discrete, made of fundamental building blocks. The scale where this would happen is called the Planck scale. The Planck length is about 10 to the minus 35 meters. That's 0.0000000000000000000000000000000000000000000001 meters. It's incomprehensibly small. For comparison, a proton is about 10 to the minus 15 meters across. The Planck length is about 20 orders of magnitude smaller than a proton. The Planck time is about 10 to the minus 44 seconds. That's how long it would take light to travel one Planck length. These scales are so small that we have no way to probe them directly. We can't build a microscope powerful enough. We can't do experiments at these energies. The energies required to probe the Planck scale are about 10 to the 19th giga-electron volts. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 10 to the 4th giga-electron volts. To probe the Planck scale, we'd need an accelerator 10,000 trillion times more powerful, so we're stuck doing theoretical work. We're building mathematical models and trying to figure out which ones make sense, which ones are internally consistent, and which ones might actually describe reality. One approach is called loop quantum gravity. This theory says that space-time is made of loops, tiny loops of space connected together in a network. Space would be fundamentally discrete, made of these loops, and the geometry of space-time would emerge from how the loops connect to each other. In loop quantum gravity, the smooth space-time we experience is an approximation that works at large scales. But zoom into the Planck scale, and you'd see the discrete structure. Space would be quantized, coming in minimum units. Time would also be quantized. There would be a shortest possible time interval, about 1 Planck time. This theory is mathematically sophisticated and has some appealing features. It doesn't require extra dimensions or exotic new particles. It's built directly on the principles of quantum mechanics and general relativity. And it predicts that the Big Bang wasn't actually a singularity, a point of infinite density. Instead, there was a big bounce. The universe collapsed to a very small but finite size, then bounced back and started expanding. But loop quantum gravity also has problems. It's very difficult to extract predictions from the theory that can be tested. The effects would only be noticeable at the Planck scale, which we can't probe experimentally. It's also not clear how to incorporate the other forces of nature, the electromagnetic, weak, and strong forces, into the same framework. And it hasn't been successfully shown that the smooth space-time of general relativity emerges from the theory at large scales. That seems like it should work, but proving it rigorously has been difficult. Another approach is string theory. String theory says that the fundamental objects in nature aren't point particles, but tiny vibrating strings. Different vibrations of these strings correspond to different particles. An electron is one vibration. A photon is another vibration. A quark is another. And crucially, one particular vibration corresponds to the graviton, the particle that would carry the gravitational force. In string theory, gravity emerges naturally from the vibrations of strings. You don't have to add it in by hand. It's automatically part of the theory. String theory requires extra dimensions of space beyond the 3 we experience. Most versions require 10 dimensions total, 9 of space and 1 of time, or 11 dimensions in some versions called M theory. The extra 6 or 7 dimensions are supposedly curled up so small we don't notice them. They're compactified at scales near the Planck length. And the geometry of spacetime, the curvature we experience as gravity, comes from how strings move and interact in this higher dimensional space. String theory is mathematically elegant. It's internally consistent in ways that other quantum gravity theories aren't. It naturally includes gravity. It unifies all the forces of nature in a single framework. The electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity all emerge from strings vibrating in different ways. The theory has a rich mathematical structure that's deeply connected to advanced mathematics. Mathematicians have discovered new theorems in pure mathematics by studying string theory. It's a beautiful theory. The history of string theory is fascinating. It didn't start as a theory of quantum gravity at all. In the late 1960s, physicists were trying to understand the strong nuclear force, the force that holds atomic nuclei together. They developed a mathematical model where particles were represented as strings. This seemed to work for certain properties of particles produced in high-energy collisions. But the string model had problems. It predicted particles that didn't exist. It required extra dimensions. And in 1973, quantum chromodynamics, a different theory, proved to be the correct description of the strong force. String theory seemed to be a dead end, but some physicists kept working on it. In 1974, John Schwartz and Joel Shirk noticed something remarkable. One of the vibration modes of the string had exactly the properties you'd expect for a graviton. String theory wasn't a theory of the strong force. It was a theory of quantum gravity. This was exciting, but the theory still had serious problems. It predicted a type of particle called a tachyon, which would travel faster than light. This is impossible, according to relativity. And the theory only worked consistently in 26 dimensions, which seemed absurd. Then, in the early 1980s, physicists discovered supersymmetry could be incorporated into string theory. Supersymmetry is a hypothetical symmetry that relates particles with different spins. Every particle would have a superpartner with a spin differing by 1/2. Electrons would have selectrons. Quarks would have squarks. Photons would have photinos. When you add supersymmetry to string theory, several things happen. The tachyon disappears. The theory becomes more mathematically consistent. And it only requires 10 dimensions instead of 26, which still seems like a lot, but is better than 26. In 1984, Michael Green and John Schwartz made another crucial discovery. They showed that certain mathematical inconsistencies that had plagued string theory could be resolved. The theory could be made completely consistent, at least mathematically. This sparked what's called the first superstring revolution. Hundreds of physicists started working on string theory. Papers poured out, exploring the theory's properties and implications. By the mid-1980s, physicists had discovered 5 different versions of superstring theory. They were all mathematically consistent, but they seemed to be different theories. This was puzzling. If string theory was the fundamental theory of nature, there should only be one version. Then, in 1995, Edward Witten proposed something radical. All 5 versions of string theory were actually different limits of a single, more fundamental theory. He called it M-theory. M-theory works in 11 dimensions, 10 of space and 1 of time. The 5 superstring theories are different ways of looking at this same underlying theory, different mathematical descriptions of the same physical reality. This was called the second superstring revolution. It suggested that string theory might truly be unique. There might be only one consistent quantum theory that includes gravity. But string theory also has serious problems as a description of reality. It makes almost no testable predictions at energies we can reach in experiments. The natural energy scale of string theory is the Planck energy, about 10 to the 19th giga-electron volts. This is the energy at which quantum effects on spacetime become important. It's the energy you'd need to probe the fundamental structure of spacetime. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 10 to the 4th giga-electron volts. To probe the Planck scale directly, we'd need an accelerator 10,000 trillion times more powerful than the LHC. Building such a machine is far beyond our current technological capabilities. You'd need a particle accelerator the size of the galaxy. The energy requirements would be astronomical. It might be beyond the capabilities of any civilization bound by the laws of physics as we understand them. The strings themselves are incredibly small, about the Planck length, which is about 10 to the minus 35 meters. That's 20 orders of magnitude smaller than a proton. We have no way to observe them directly. String theory does make some predictions about particle physics at lower energies. It predicts supersymmetry, for instance. Every particle should have a superpartner. But these superpartners haven't been found. The LHC has searched for them extensively. If they exist, they must be heavier than anything the LHC can produce. Or they don't exist at all, which would be a serious problem for string theory. String theory also has what's called the landscape problem. The equations of string theory have an enormous number of possible solutions. Possibly 10 to the 500 or more different solutions. Each solution describes a different possible universe with different physical constants and different laws of physics. Different particles, different forces, different values for things like the masses of particles and the strengths of forces. Which solution describes our universe? Nobody knows. There's no principle within string theory that picks out our universe as special. Some physicists have argued that maybe all of these solutions are real. Maybe each one describes a different universe in a vast multiverse. Our universe just happens to be one particular point in this landscape of possibilities. We exist in this particular universe because the physical constants happen to allow stars, planets, and life to form. In other universes with different constants, life might not be possible, so there's nobody there to observe them. This kind of anthropic reasoning troubles many physicists. It seems to give up on the goal of explaining why the laws of physics have the specific form they do. Instead, it says the laws are essentially random, different in different universes. And we live in one of the rare universes where the laws allow life. It's not a satisfying explanation. It doesn't predict anything. It doesn't explain anything. It can't be tested. You can't observe other universes that are forever beyond our cosmic horizon. You can't verify that they exist. The multiverse becomes a philosophical idea rather than a scientific theory. And there's an even more fundamental problem with string theory. Without testable predictions, how do we know it's right? It's mathematically beautiful. It's logically consistent. It unifies forces in an elegant way. It has deep connections to pure mathematics, but beauty and elegance aren't proof of truth. History is full of beautiful theories that turned out to be wrong. Physics requires experimental verification. We need to test theories against reality. And for string theory, that's incredibly difficult, maybe impossible with current or foreseeable technology. Some physicists argue that string theory has become more of a mathematical framework than a physical theory. It's produced important insights into mathematics and theoretical physics. It's given us tools for doing calculations in quantum field theory. It's revealed deep connections between different areas of physics and mathematics. These are valuable contributions. But, as a theory of fundamental reality, as a quantum theory of gravity that explains what spacetime really is, it remains unproven. It might be right. It might be a beautiful mathematical structure that happens to describe how the universe actually works. Or it might be a beautiful mathematical structure that has nothing to do with physical reality. We simply don't know yet. There's also a more radical idea that's gained traction in recent years. Maybe space-time isn't fundamental at all. Maybe space and time are emergent properties that arise from something deeper, something that doesn't look like space or time at all. This is the idea behind approaches with names like ER equals EPR, holography, and entanglement entropy. Here's the basic idea. Quantum mechanics allows for a strange phenomenon called entanglement. Two particles can be entangled such that measuring one instantly affects the other, no matter how far apart they are. Let me explain what this means. Suppose you have two electrons that were created together in a specific quantum state. They might be entangled such that they have opposite spins. If you measure one and find it spinning up, the other will instantly be spinning down. If you measure the first one and find it spinning down, the other will be spinning up. But here's the weird part. Before you measure, neither electron has a definite spin. Each electron is in a quantum superposition of spinning up and spinning down simultaneously. It's not that one electron is secretly spinning up and the other is secretly spinning down, and you just don't know which is which. They genuinely don't have definite spins until you measure. When you measure one electron and force it to have a definite spin, the other electron instantly acquires the opposite spin, no matter how far apart they are, even if they're on opposite sides of the galaxy. This isn't communication faster than light, because you can't control the outcome of your measurement. You can't send information this way. But it is a correlation that exists across space without anything traveling through the space between the particles. In 1935, Einstein and two colleagues, Boris Podolsky and Nathan Rosen, wrote a paper describing this phenomenon. They argued it showed quantum mechanics was incomplete. They thought the correlations must be explained by some hidden information the particles carried with them, some hidden variables. Einstein called entanglement spooky action at a distance. He didn't like it. It seemed to violate locality, the idea that objects can only be directly influenced by their immediate surroundings. But experiments have shown the correlations are real, and they can't be explained by hidden variables or by information the particles carried with them when they were created. Entanglement is a genuine feature of quantum mechanics. It's been verified in countless experiments. Also, in 1935, Einstein and Nathan Rosen wrote another paper about solutions to general relativity that contained wormholes. Shortcuts through spacetime, connecting distant regions. These became known as Einstein-Rosen bridges, or ER bridges. In this solution, you have two black holes connected by a bridge through spacetime. If you fell into one black hole, you might emerge from the other. It's a shortcut through space. But the wormholes in the Einstein-Rosen solution were unstable. They would collapse before anything could pass through them. You'd be crushed in the middle, so they weren't useful for travel, even in principle. For decades, these two ideas, entanglement and wormholes, were studied separately. They seemed completely unrelated. Entanglement is a quantum phenomenon. Wormholes are a general relativistic phenomenon. But in recent years, physicists have wondered if there might be a connection between them. The idea is summarized by the equation ER equals EPR. ER stands for Einstein-Rosen bridges, the wormholes. EPR stands for Einstein-Podolsky-Rosen, the entanglement. The suggestion is that when two particles are entangled, they're connected by a tiny wormhole, a microscopic thread of space-time linking them. This sounds crazy at first. How can a quantum correlation between particles be the same thing as a geometric connection through space? But there's serious theoretical evidence for this idea. It comes from studying black holes and from thinking about the holographic principle. Here's one piece of evidence. Consider two black holes that are maximally entangled with each other. This is a specific quantum state where the two black holes are as correlated as they can possibly be. You can describe this quantum state using the mathematics of quantum mechanics. It's called an Einstein-Podolsky-Rosen pair of black holes. But you can also describe the same system using general relativity. Two black holes connected by a wormhole, an Einstein-Rosen bridge. The mathematics suggests these are the same thing. An entangled pair of black holes is a wormhole connecting them. The quantum description and the geometric description are two ways of talking about the same physical reality. If this is true, it has profound implications. It suggests that when any two particles are entangled, they're connected by a tiny wormhole. Even though the wormhole is far too small to see or to send anything through. And if connections through space are the same thing as quantum entanglement, then space-time itself might be woven from entanglement. The geometry of space, the distances between points, might emerge from the pattern of entanglement between particles. This would mean space-time is not fundamental. It's emergent. It arises from something more basic, something quantum mechanical. Space would be an illusion at the fundamental level, a useful way of describing something more fundamental. Distance would emerge from the degree of entanglement. Points that are highly entangled would be close together in the emergent space. Points that aren't entangled would be far apart. Time would also emerge from how entanglement changes, from the evolution of quantum correlations. This is a radically different picture of reality. In this view, asking what happened before the Big Bang might not even make sense, because time itself is emergent. It only exists when you have enough quantum entanglement to create something that looks like time. At the most fundamental level, there might be no time, no space, just quantum information, just patterns of entanglement. And the space-time we experience, the arena where events happen, would be a large-scale approximation, something that emerges when you have many particles entangled in specific ways. This is highly speculative. It's not a complete theory yet, but it's motivated by serious theoretical work and by discoveries about the nature of black holes and quantum information. There's been significant progress in recent years in showing how spacetime can emerge from entanglement in simplified toy models. These are not realistic models of our universe, but they're mathematically well-defined systems where you can prove rigorously that space emerges from entanglement. In these models, you start with a collection of quantum systems that are entangled with each other in specific patterns. No space, just quantum states and entanglement. Then you can show that if you zoom out and look at the system from a distance, ignoring the microscopic quantum details, it looks like particles moving through space. The space is emergent. It's not put in by hand. It arises automatically from the pattern of entanglement. If this picture is right, and we can extend it from toy models to realistic models of our universe, it would completely change how we think about spacetime. We'd have to think of spacetime as a kind of phase of matter, like how water can exist as ice, liquid, or steam. Depending on temperature and pressure, maybe quantum information can exist in different phases. In one phase, it looks like spacetime with particles moving through it. In another phase, maybe at very high energies or very small distances, it wouldn't look like spacetime at all. It would look like something completely different. The Big Bang might not be the beginning of time. It might be a phase transition, a moment when quantum information rearranged itself from one phase into another, from a phase where time and space don't exist into a phase where they do. These are speculative ideas, but they're being actively explored by some of the best theoretical physicists in the world. And they point to a possibility that's both exciting and deeply unsettling. Everything we think we know about space and time might be wrong at the fundamental level. They might not be the basic building blocks of reality. They might be emergent, like temperature emerging from molecular motion, appearing only at large scales, from underlying quantum processes that look nothing like space or time. Let's talk about one of the deepest mysteries involving spacetime: the black hole information paradox. This is a problem that's haunted physics for decades, and it gets right to the heart of what spacetime is. Black holes are regions of spacetime curved so extremely that not even light can escape. They form when massive stars collapse at the end of their lives, or when enormous amounts of matter get compressed into a tiny volume. But the history of black holes is fascinating, because Einstein himself didn't believe they were real. Just a few months after Einstein published general relativity in 1915, a German physicist named Karl Schwarzschild found an exact solution to Einstein's equations. He was serving in the German army during World War I, calculating artillery trajectories by day, but at night he was doing theoretical physics. Schwarzschild found a solution describing the spacetime around a perfectly spherical, non-rotating mass. This is now called the Schwarzschild solution, and it's the simplest example of a black hole. The solution has a special radius, now called the Schwarzschild radius. For any mass, there's a radius where if you compressed all that mass inside it, something strange happens. At that radius, the escape velocity equals the speed of light. Inside that radius, nothing can escape, not even light. Outside that radius, things can escape if they're moving fast enough. For Earth, the Schwarzschild radius is about 9 millimeters, less than half an inch. If you could magically compress Earth to that size, it would become a black hole. But Earth's actual radius is about 4,000 miles, so we're nowhere close. For the Sun, the Schwarzschild radius is about 2 miles, less than 2 miles. The Sun's actual radius is about 430,000 miles, so again, nowhere close. But for objects massive enough and dense enough, this can actually happen. When a massive star runs out of fuel, it can no longer support itself against gravity. The core collapses. If the star is massive enough, nothing can stop the collapse. The core crushes down past the Schwarzschild radius. A black hole forms. Schwarzschild sent his solution to Einstein in December 1915. Einstein was impressed by the mathematics, but he didn't think black holes could actually exist in nature. He thought something would always prevent the collapse. In 1939, Einstein even published a paper arguing that black holes couldn't form. His reasoning was that as matter collapsed, it would spin faster and faster, like an ice skater pulling in their arms. Eventually, it would be spinning so fast that centrifugal force would prevent further collapse. He was wrong. J. Robert Oppenheimer, who would later lead the Manhattan Project, showed in 1939 that there was no way to prevent collapse if the star was massive enough. Nothing could stop it. The star would collapse past the Schwarzschild radius and keep collapsing until all its mass was concentrated at a point. Oppenheimer's calculation was correct, but he couldn't find a flaw in Einstein's mathematics either. The equations were right. General relativity really did predict these objects. Einstein died in 1955, never accepting that black holes were real. For the next couple of decades, most physicists remained skeptical. Black holes seemed too strange, too extreme. They violated intuitions about how the universe should work. But observations started to pile up. In the 1960s, astronomers discovered quasars, incredibly bright objects in distant galaxies that were pouring out enormous amounts of energy from very small regions of space. The only explanation that made sense was that these were supermassive black holes, millions or billions of times the mass of the Sun, feeding on gas and dust. The material falling into the black hole would heat up to millions of degrees as it spiraled inward. Before crossing the event horizon, this superheated gas would radiate enormous amounts of energy, more energy than all the stars in the galaxy combined. And theorists were making progress, understanding what black holes really meant for physics. In 1965, Roger Penrose proved a remarkable theorem. He showed that once a star collapses past a certain point, the formation of a singularity is mathematically unavoidable. It's not a matter of the star being perfectly spherical or having special properties. Any collapsing star beyond a certain mass would form a singularity. The laws of physics, as described by general relativity, literally forced it to happen. Stephen Hawking extended this work. In the late 1960s and early 1970s, working with Penrose and others, he proved that singularities are generic features of general relativity. They don't just appear in black holes. The Big Bang itself, the beginning of the universe, was a singularity, a point of infinite density and infinite curvature, where time itself began. Hawking showed that if you run the expansion of the universe backward in time using Einstein's equations, you inevitably reach a singularity. There's no way to avoid it within the framework of general relativity. This was deeply troubling. General relativity had been incredibly successful at describing gravity, space-time, and the motion of objects from planets to galaxies. But the theory itself predicted places where it broke down, places where the equations gave infinite answers and stopped making sense. Singularities were like signs posted in the mathematics saying, "Beyond this point, physics doesn't work. Beyond this point, you need a new theory." According to general relativity, a black hole has a boundary called the event horizon. Once you cross the event horizon, you can never get back out. All paths through space-time led inward toward the singularity at the center. Even if you're traveling at the speed of light, you'd still be pulled toward the center. Inside the event horizon, space-time is so warped that the direction toward the singularity becomes more like a direction in time than a direction in space. Falling into the singularity becomes as inevitable as moving forward in time. You can't avoid it any more than you can avoid tomorrow. At the singularity itself, the curvature of space-time becomes infinite. The equations of general relativity break down. They produce infinities, which means they're no longer valid. General relativity is telling us that there's something it can't describe, that a deeper theory is needed. But the real mystery is what happens to information that falls into a black hole. In quantum mechanics, information is never destroyed. If you know the exact quantum state of a system at one time, you can, in principle, calculate its exact quantum state at any other time. The evolution is deterministic, even though individual measurements give probabilistic results. But black holes seem to violate this principle. If you throw a book into a black hole, all the information in that book, every arrangement of atoms, every pattern of ink on the pages, falls past the event horizon and seems to disappear forever. The black hole doesn't care what you threw into it. It only has a few properties: mass, charge, and spin. Everything else is lost. This bothered physicists for a long time. It seemed to violate a fundamental principle of quantum mechanics. Then, in 1974, Stephen Hawking made a discovery that made the problem even worse. Hawking showed that black holes aren't completely black. They emit radiation. This became known as Hawking radiation. Here's how it works. Quantum mechanics says that empty space isn't really empty. It's filled with quantum fluctuations. Pairs of particles and antiparticles that pop into existence for incredibly brief moments before annihilating each other. This happens everywhere, all the time. Near a black hole's event horizon, something special can happen. A particle-antiparticle pair can form just outside the horizon. One particle falls into the black hole. The other escapes to infinity. From far away, it looks like the black hole is emitting radiation. The energy for this radiation comes from the black hole's mass. So as a black hole emits Hawking radiation, it slowly loses mass. It evaporates. For large black holes, this process is incredibly slow. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate. That's far longer than the current age of the universe. But in principle, given enough time, any black hole will completely evaporate away. Here's the problem. Hawking radiation appears to be completely random. It's thermal radiation. The same kind of radiation emitted by any hot object. It doesn't carry any information about what fell into the black hole. So if you throw a book into a black hole and wait for the black hole to evaporate, the Hawking radiation that comes out contains none of the information that was in the book. The information seems to be destroyed. This violates quantum mechanics. This is the black hole information paradox. Does quantum mechanics break down at black holes? Or is general relativity wrong about what happens inside black holes? Or is there some way information can escape that we haven't figured out yet? Physicists have been arguing about this for 50 years. It's one of the deepest problems in theoretical physics. And solving it requires understanding what space-time really is at the quantum level. There's been significant progress in recent years. Most physicists now think the information isn't actually destroyed. Instead, it's encoded in the Hawking radiation in a very subtle, complex way. The radiation isn't truly random. It only looks random because the information is scrambled so thoroughly. This solution comes from ideas about holography and quantum entanglement. The idea is that all the information about what's inside a black hole is actually encoded on its event horizon. The event horizon acts like a hologram, a two-dimensional surface that contains all the information about the three-dimensional interior. As the black hole evaporates, this information is gradually transferred to the outgoing Hawking radiation. But it's encoded in correlations between different particles, in the patterns of entanglement. You'd have to collect and analyze all the radiation from the entire evaporation process to recover the original information. This solution is called the island formula, and it's been worked out in detail for simplified models of black holes in the last few years. It suggests that general relativity and quantum mechanics can be reconciled. Information isn't destroyed, but the way it's preserved is far more subtle than anyone imagined. And crucially, this solution depends on the idea that space-time is not fundamental, that it emerges from quantum entanglement, that the connections between different regions of space are actually quantum correlations between the particles in those regions. This brings us back to the fundamental question: what is space-time? The bottom line is this: we don't know what it's made of. We don't know if it's fundamental or emergent. We don't know what happened at the Big Bang, when the equations predict a singularity where physics breaks down. We don't fully understand what happens inside black holes. We have equations that describe its behavior brilliantly. Einstein's general relativity is one of the most successful theories in the history of science. It's been tested countless times and passed every test. We can measure space-time. We can photograph it, bending around massive objects. We can detect gravitational waves rippling through it. We can use it to build technology like GPS that works perfectly. But we don't have a complete theory that explains its true nature. We don't have a quantum theory of gravity. We don't know what happens at the Planck scale, where quantum effects should become important. This isn't a failure of science. This is where we are. This is the frontier of human knowledge. Every great theory in science eventually reaches a boundary where it can't go further without something new. Newton's laws reached that boundary when scientists started measuring the speed of light precisely and noticed the anomaly in Mercury's orbit. They needed Einstein's relativity to go further. Quantum mechanics and relativity reached that boundary when scientists started thinking seriously about black holes and the Big Bang. Now we need something new, a quantum theory of gravity, a description of what space-time is at the Planck scale. Somewhere beyond that boundary is the answer, an understanding of what happened at the beginning of the universe, the resolution of the information paradox. Maybe a unified theory that describes all forces and particles, maybe a multiverse, maybe something we haven't imagined yet. But before we go any further into these deep mysteries, let's pause and appreciate something remarkable. This idea we don't fully understand, this theory that breaks down at singularities and might have quantum corrections we can't calculate yet, is something we use every single day. General relativity isn't just an abstract theory for understanding black holes and the Big Bang. It affects your life in concrete, practical ways. Let's start with the most obvious example, GPS. Your phone, your car's navigation system, any device that tells you where you are on Earth, uses a network of satellites orbiting the planet. There are currently about 30 GPS satellites circling Earth at an altitude of about 12,400 miles. These satellites constantly broadcast signals containing two critical pieces of information: the exact time, according to atomic clocks on board the satellites, and the satellite's precise position. Your GPS device receives signals from at least 4 satellites. It measures how long each signal took to arrive, and it uses that timing information to calculate your position. The speed of light is constant, about 186,000 miles per second. If you know how long a signal took to arrive, and you know it traveled at the speed of light, you can calculate how far away the satellite was when it sent the signal. With signals from 4 satellites, you can pinpoint your position in 3-dimensional space. It's elegant geometry. But there's a problem. The atomic clocks on the satellites don't tick at the same rate as clocks on the ground. There are 2 effects from relativity at work here. First, the satellites are moving fast relative to the ground, about 8,700 miles per hour. According to special relativity, time runs slower for moving objects. From the perspective of someone on the ground, the satellite clocks should be ticking slightly slower. This is called time dilation due to velocity. The effect is tiny but measurable. The satellite clocks lose about 7 microseconds per day compared to clocks on the ground. That's 7 millionths of a second per day. But there's a second effect that's even larger. The satellites are higher up in Earth's gravitational field. They're farther from Earth's center of mass, so they experience weaker gravity. According to general relativity, time runs faster in weaker gravitational fields. From the perspective of someone on the ground, the satellite clocks should be ticking slightly faster. This is called gravitational time dilation. The satellite clocks gain about 45 microseconds per day compared to clocks on the ground. When you add these 2 effects together, the velocity slowing down time and the weaker gravity speeding it up, the satellite clocks run about 38 microseconds per day, faster than clocks on the ground. 38 microseconds doesn't sound like much, but light travels about 300 meters, about 984 feet, in 1 microsecond. If the GPS system didn't correct for these relativistic effects, your position would be off by about 7 miles. Within hours, GPS would be completely useless. Your navigation would tell you you're in the wrong city. Within days, it would tell you you're in a different state. But the GPS system does account for relativity. The satellite clocks are programmed to tick at a slightly different rate to compensate for both special and general relativistic effects. When the satellites are on the ground being prepared for launch, their clocks are set to run slow. Then, when they're in orbit, the relativistic effects speed them up to exactly the right rate. This means every time you use GPS, every time you check your location on your phone or follow directions in your car, you're using Einstein's theory of relativity. You're using the fact that time runs at different rates depending on how fast you're moving and how deep you are in a gravitational well. This is a direct, practical application of our understanding of spacetime. It's not just theoretical. It's technology that billions of people use every day. But GPS is just the most obvious example. There are other ways general relativity affects modern life. Astronomers use gravitational lensing to study the universe. When light from a distant galaxy passes near a massive object, like another galaxy, or a cluster of galaxies, the light's path bends. The massive object acts like a lens, focusing and magnifying the light from the distant galaxy. This allows us to see galaxies that would otherwise be too faint to detect. We can study the early universe, galaxies that formed when the universe was young, by using gravitational lensing to magnify them. We can also use lensing to map dark matter. Dark matter doesn't emit light, so we can't see it directly. But it has mass, so it curves spacetime. When light passes through a region with dark matter, its path bends. By studying how light from background galaxies is distorted, we can map where the dark matter is and how much of it there is. This has revealed that dark matter makes up about 85% of all matter in the universe. We don't know what dark matter is made of, but we know it's there because we can see its gravitational effects on space-time. Gravitational waves are another tool. Since the first detection in 2015, we've detected dozens of gravitational wave events, mostly from pairs of black holes spiraling into each other and merging, but also from pairs of neutron stars colliding. These observations tell us things we couldn't learn any other way. We can measure the masses of black holes. We can test whether general relativity accurately describes what happens in extremely strong gravitational fields. We can study the equation of state of neutron star matter, the densest material in the universe. In 2017, gravitational wave detectors picked up a signal from two neutron stars colliding. At the same time, telescopes around the world observed a burst of gamma rays, X-rays, and visible light from the same event. This was the first time we'd observed the same astronomical event with both gravitational waves and electromagnetic radiation. The collision created heavy elements like gold and platinum. By studying the light from the explosion, astronomers could see the signatures of these elements being synthesized. This confirmed that neutron star collisions are where most of the heavy elements in the universe come from, including the gold in your jewelry and the platinum in your electronics. More dramatically, gravitational waves allow us to test general relativity in ways that weren't possible before. When two black holes merge, they produce a specific pattern of gravitational waves. The frequency and amplitude of the waves depend on the masses of the black holes, how fast they're spinning, and how their spins are oriented. General relativity makes precise predictions about what this signal should look like, and every gravitational wave event we've detected has matched those predictions perfectly. The theory works even in the most extreme conditions we can observe. Black holes, dozens of times the mass of the Sun, moving at significant fractions of the speed of light, producing more power in gravitational waves for a brief moment than all the stars in the observable universe combined. Einstein's equations describe it all. There are also more exotic possible uses. Some physicists have speculated about using understanding of space-time curvature to create advanced propulsion systems. If you could manipulate space-time, curve it in specific ways, you might be able to create something like a warp drive. Contract space in front of a spacecraft and expand it behind. This is purely theoretical. The energy requirements would be enormous, possibly requiring more energy than exists in the entire observable universe. And there are serious questions about whether it's even possible in principle. General relativity allows such solutions mathematically, but that doesn't mean they can be realized in practice. But the point is, understanding space-time has practical implications, not just for navigation and astronomy, but potentially for future technologies we can barely imagine. Let me give you some perspective on why solving the deeper mysteries matters. Why should you care about whether space-time is made of loops or strings or entanglement? Why does it matter what happened at the Big Bang or whether black holes preserve information? These seem like abstract questions, far removed from everyday life. But solving these mysteries could change everything. First, understanding what space-time is at the fundamental level would complete the picture of reality that physics has been building for centuries. Right now, we have two great theories that describe the universe. General relativity describes gravity and the large-scale structure of the cosmos. Quantum mechanics describes particles and forces at small scales. Both theories are extraordinarily successful. They've been tested countless times and have never failed within their domains. General relativity has passed every test we've thrown at it. The bending of starlight during eclipses, the precession of Mercury's orbit, gravitational time dilation verified by atomic clocks, the existence of black holes, the expansion of the universe, gravitational waves from colliding black holes, the shadow of the supermassive black hole in M87. Every prediction has been confirmed. Quantum mechanics is equally successful. It explains the structure of atoms, the periodic table of elements, chemical bonds, the behavior of materials from semiconductors to superconductors, lasers, nuclear reactions, the fundamental particles and forces. Every piece of modern technology, from computers to medical imaging to solar panels, relies on quantum mechanics. It's been tested to extraordinary precision, and it always works. But these two theories can't both be right in their current forms, because they contradict each other. General relativity treats space-time as smooth and continuous. You can zoom in as much as you want, and it's still smooth. There's no smallest distance. Space is infinitely divisible. Quantum mechanics says everything comes in discrete units at small enough scales. Energy is quantized. Matter is made of discrete particles. There's a smallest unit of action, Planck's constant. General relativity is deterministic. If you know the curvature of space-time and the positions and velocities of all objects at one moment, you can calculate exactly where everything will be at any other moment. The future is completely determined by the present. Quantum mechanics is probabilistic. You can only calculate the probability of different outcomes. Individual measurements give random results, even though the underlying wave function evolves deterministically. The future is not completely determined by the present. General relativity says information is preserved in the smooth evolution of space-time. Quantum mechanics says information is preserved in the unitary evolution of quantum states. But black holes seem to destroy information according to general relativity, violating quantum mechanics. These are fundamentally different worldviews, and they clash when you try to apply both to the same situation. Like the interior of a black hole, where gravity is so strong that quantum effects on space-time should be important. Or the Big Bang, where the entire universe was compressed to such a small size that quantum effects must have been crucial. A quantum theory of gravity would unify these two pillars of physics. It would give us a single, consistent framework for understanding the universe at all scales, from the smallest particles to the largest structures, from the first moment after the Big Bang to the ultimate fate of black holes. It would be the culmination of a quest that's been going on since the early 20th century. Since physicists first realized that quantum mechanics and general relativity, despite their individual successes, were incompatible at the deepest level. And it would almost certainly reveal new physics, new phenomena we haven't imagined yet. History strongly suggests this. Every time we've unified different areas of physics, we've discovered new things. When James Clerk Maxwell unified electricity and magnetism in the 1860s, it seemed like abstract theoretical work. He showed that electric fields and magnetic fields were different aspects of a single electromagnetic field. He wrote down equations describing how electromagnetic fields propagate. Those equations predicted that electromagnetic waves should exist. Waves of electric and magnetic fields rippling through space. And these waves should travel at a specific speed, which turned out to be exactly the speed of light. Maxwell realized that light itself was an electromagnetic wave. This was a stunning unification. Optics, the study of light, and electromagnetism, the study of electric and magnetic forces, were the same thing. But the practical implications went far beyond this theoretical insight. Maxwell's equations led to the discovery of radio waves, then to radio communication, then to radar, television, microwaves, Wi-Fi, cell phones, satellite communication. Every piece of wireless technology you use exists because Maxwell unified electricity and magnetism. Nobody in the 1860s could have predicted this. They were doing pure theoretical physics, trying to understand fundamental forces. But their work led to technologies that transformed civilization. When quantum mechanics was developed in the early 20th century, it also seemed impossibly abstract, divorced from practical concerns. Physicists were trying to understand the structure of atoms and the behavior of light. They discovered that energy comes in discrete packets, that particles have wave properties, that you can't simultaneously know a particle's position and momentum with arbitrary precision. None of this seemed useful for anything practical. It was pure fundamental physics, trying to understand the nature of reality at the smallest scales. But quantum mechanics led to our understanding of how atoms bond to form molecules, how electrons behave in materials, how semiconductors work, and that led to transistors, then to integrated circuits, then to computers, then to smartphones, the internet, modern medicine, renewable energy. Every piece of modern technology relies on quantum mechanics. Your phone, your computer, LED lights, solar panels, medical imaging machines, GPS satellites. All of it depends on physics that seemed purely theoretical a century ago. When Einstein developed relativity, it seemed like the most impractical theory imaginable. Pure intellectual exercise with no connection to everyday life. Time running at different rates, depending on motion and gravity. Space and time being unified into spacetime. Mass curving spacetime. These seemed like exotic ideas with no practical application. But GPS satellites rely on relativistic corrections. Without accounting for both special and general relativity, GPS would be useless within hours. Nuclear energy comes from Einstein's equation, E equals mc squared, the equivalence of mass and energy. Every nuclear power plant, every nuclear weapon, every star in the universe demonstrates this equivalence. And gravitational lensing, black holes, gravitational waves, the expansion of the universe, all predicted by general relativity, have become tools for astronomy and cosmology. A quantum theory of gravity could lead to technologies we can't even imagine right now. If space-time is quantized, made of discrete units, maybe we could learn to manipulate those units. Maybe we could create localized regions of altered space-time, artificial gravity for spacecraft. shielding from gravitational forces. New types of sensors that detect space-time curvature directly. If wormholes can exist and be stabilized, maybe we could use them for communication or even travel. Send signals through space-time shortcuts instead of through normal space. If the holographic principle is right, and all information in a volume is encoded on its boundary, maybe we could build computers that use this principle. Holographic data storage operating on fundamentally new principles. These are wild speculations. Most physicists think they're probably impossible. The energy scales involved in manipulating space-time at the quantum level are so enormous that we might never be able to harness them practically. You'd need energies comparable to the Planck energy, about 10 to the 19th giga-electron volts. For comparison, the entire rest mass energy of Earth, if you converted all of Earth into pure energy, is about 10 to the 41 joules. The Planck energy is about 2,000 joules concentrated in a single quantum event. That might not sound like much. 2,000 joules is about the energy needed to lift a small car 1 meter. But concentrating that energy into a single quantum interaction at the Planck scale would require extraordinary technology. So maybe these applications are forever beyond reach. But the point is, we don't know. And history shows that understanding fundamental physics often leads to applications no one predicted. Maxwell wasn't trying to invent radio. He was trying to understand electric and magnetic fields. The quantum pioneers weren't trying to invent computers. They were trying to understand atoms. Einstein wasn't trying to create GPS or nuclear energy. He was trying to understand gravity and the nature of space-time. But their pure theoretical work, driven by curiosity about how the universe works, led to technologies that changed civilization. Maybe a quantum theory of gravity will be the same. Maybe understanding what space-time really is will lead to technologies we can't even conceive of right now. Or maybe it won't. Maybe it will remain pure theoretical knowledge. But even if it never leads to practical applications, it would still be worth pursuing, because it would answer some of the deepest questions humans have ever asked. When James Clerk Maxwell unified electricity and magnetism in the 1860s, it seemed like abstract theoretical work, but it led to radio, television, telecommunications, all of modern electronics. Every piece of electronic technology you use exists because Maxwell unified those forces. When quantum mechanics was developed in the early 20th century, it seemed impossibly abstract and divorced from practical concerns. But it led to semiconductors, transistors, lasers, computers. Every piece of modern technology relies on quantum mechanics. Your phone, your computer, LED lights, medical imaging, solar panels, all of it. When Einstein developed relativity, it seemed like the most impractical theory imaginable. Pure intellectual exercise, with no connection to the real world. But GPS satellites rely on relativistic corrections to work properly. Nuclear energy comes from Einstein's equation, E equals mc squared, showing that mass and energy are equivalent. A quantum theory of gravity could lead to technologies we can't even imagine right now. If space-time is quantized, maybe we could learn to manipulate it. Maybe we could create artificial gravity or control the flow of time in localized regions. If wormholes can exist and be stabilized, maybe we could use them for travel or communication. These are wild speculations. Most physicists think they're probably impossible. The energy scales involved in manipulating space-time at the quantum level are so enormous that we might never be able to harness them practically. But the point is, we don't know. And history shows that understanding fundamental physics often leads to applications no one predicted. More importantly, understanding space-time would answer some of the deepest questions humans have ever asked. Where did the universe come from? What happened before the Big Bang? Will the universe end? And if so, how? What happens inside a black hole? Why does time flow in one direction, from past to future? Why are there 3 dimensions of space and 1 of time, instead of some other combination? Why do the laws of physics have the form they do? Could they have been different? These questions have fascinated humans for thousands of years. Every culture throughout history has grappled with them. Every civilization has had origin myths, stories about how the world began. The ancient Greeks had their creation myths involving chaos and the Titans. Norse mythology had the world emerging from the void of Ginnungagap. Hindu cosmology has cycles of creation and destruction spanning billions of years. The Abrahamic religions have the creation story in Genesis. These stories reflect humanity's deep need to understand where we came from, to know how the universe began. Every religion has grappled with the nature of time and existence. Is time real or illusory? Does it have a beginning? Will it have an end? Philosophers have debated these questions for millennia. The ancient Greek philosopher Parmenides argued that change is impossible, that time is an illusion. Heraclitus argued the opposite, that everything is constantly changing, that you can never step in the same river twice. Plato thought time was created along with the universe, that it didn't exist before creation. Aristotle thought time had no beginning, that it stretched infinitely into the past. Medieval philosophers debated whether God existed in time or outside of time, whether the universe had a beginning or had always existed. Kant argued that space and time were not features of the universe itself, but structures of human perception, ways our minds organize sensory experience. For most of history, these questions were in the realm of philosophy and religion. Science couldn't address them. We didn't have the tools. We didn't have the knowledge. We could only speculate. But now, for the first time in human history, we're close to being able to answer these questions scientifically. We have mathematical frameworks that might describe what happened at the Big Bang. Loop quantum gravity suggests the Big Bang was actually a big bounce. The universe contracted to a very small but finite size, then bounced back and started expanding. There might be no singularity, no moment of infinite density, and there might be a previous universe that existed before the bounce. We have theories that might describe what happens inside black holes. The interior might contain a bridge to another region of space-time, or it might contain a baby universe budding off from our own, or the singularity might be replaced by something else, some quantum structure that doesn't have infinite density. We have theories about why time has a direction. This is called the arrow of time. Entropy, the measure of disorder, always increases with time. Eggs break, but don't spontaneously reassemble. Heat flows from hot to cold, not the reverse. We remember the past, but not the future. Why? The second law of thermodynamics says entropy increases. But where does this law come from? It might be connected to the Big Bang. The early universe had extremely low entropy. Everything was smooth and uniform. As the universe evolved, entropy increased. Structure formed. Galaxies, stars, planets. Life emerged. The arrow of time points in the direction of increasing entropy, and that direction was set by the initial conditions at the Big Bang. A quantum theory of gravity might explain why the Big Bang had low entropy, why the universe started in such a special state. We have theories about why there are 3 dimensions of space. String theory requires extra dimensions, but suggests they're compactified, curled up small. We experience 3 large spatial dimensions because that's the stable configuration. Other numbers of dimensions might be unstable or might not allow complex structures to form. Anthropic reasoning suggests we observe 3 spatial dimensions because that's what's compatible with life. In 2 dimensions, complex structures like brains can't exist. The topology is too constrained. In 4 or more spatial dimensions, atoms might be unstable. Planetary orbits might be unstable. So we exist in 3 spatial dimensions because that's where life can exist. Whether these answers are right, we don't know yet. But we're asking the questions scientifically. We're developing mathematical frameworks. We're making predictions that might be testable. This is remarkable progress. These are questions humans have pondered since we first became conscious, since we first looked up at the stars and wondered where it all came from. And now, we're close to having scientific answers. Not just philosophical speculation, but mathematical theories that make concrete predictions. A quantum theory of gravity could tell us what happened at the Big Bang, whether time had a beginning or exists eternally, whether our universe is the only one or part of a larger multiverse. It could describe the interior of black holes, tell us whether information is preserved or destroyed, reveal whether singularities really exist or are artifacts of our incomplete theories. It could explain why time flows forward, why we remember the past but not the future, why cause precedes effect. It could tell us whether the laws of physics are unique, whether they had to be this way or could have been different, whether universes with different laws are possible. These would be among the greatest intellectual achievements in human history. Understanding the fundamental nature of reality at the deepest level, answering questions that have puzzled humanity since we first became conscious. And there's something profound about the fact that we can answer these questions. That the universe is comprehensible to us. We're made of atoms and molecules. We evolved on a small planet orbiting an ordinary star. Our brains are biological computers optimized by evolution for survival and reproduction in the African savanna. There's no obvious reason why we should be able to understand quantum mechanics or general relativity or the Big Bang. These are far outside the environment our brains evolved to deal with. Yet, we can understand them. We've figured out the mathematical laws governing the universe. We've tested those laws and found them to be correct. We've used them to make predictions, and those predictions have been confirmed. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. We're tiny creatures on a small planet. The universe is vast, beyond imagination, about 93 billion light-years across, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Most of space is empty vacuum. Most of the universe is dark matter and dark energy that we don't understand. We're an infinitesimal fraction of what exists. Yet, we've measured the curvature of spacetime. We've detected ripples in that spacetime from black holes colliding a billion light-years away. We've imaged the shadows of black holes at the centers of galaxies. We've traced the history of the universe back to fractions of a second after the Big Bang. This is extraordinary. It suggests that the universe is fundamentally knowable, that the laws of physics are the same everywhere, that we can figure them out through careful observation, experimentation, and reasoning. It should give us hope. We're not helpless in the face of cosmic mysteries. We can understand. We have understood. And we'll continue to understand more. The fact that we don't yet know what space-time is made of isn't a failure. It's an opportunity. It's a frontier waiting to be explored. And exploring that frontier, developing a quantum theory of gravity, answering these deep questions about the nature of reality, would be one of humanity's greatest achievements. Not because it would make us rich or powerful, but because it would satisfy our deepest curiosity about the universe we live in. Before we finish, let's talk about what we do know. Despite all the mysteries, despite all the unanswered questions, we've learned an enormous amount about space-time. We know it's real. It's not just a mathematical abstraction or a convenient way of describing things. It's a physical entity that can be measured and observed. We know mass and energy curve, space-time. The more mass concentrated in a region, the more curved space-time becomes in that region. This curvature is what we experience as gravity. The sun curves space-time around it. Earth moves through that curved space-time, following a geodesic, the straightest possible path. That curved path is Earth's orbit. Black holes are regions where space-time is curved so extremely that it closes in on itself. Not even light can escape. We know space-time is dynamic. It can change over time. It can ripple. It can expand. Gravitational waves are ripples in space-time itself. When massive objects accelerate, like two black holes spiraling into each other, they create waves that propagate outward at the speed of light. These waves stretch and squeeze space as they pass. We've detected these waves. We've measured them with extraordinary precision. They match the predictions of general relativity perfectly. We know the universe is expanding. Space-time itself is growing larger. The distance between galaxies is increasing, not because galaxies are moving through space, but because space itself is expanding between them. This expansion was discovered in the 1920s and has been measured with increasing precision ever since. We know the universe is about 13.8 billion years old. We know it started from an extremely hot, dense state and has been expanding and cooling ever since. We know this expansion is accelerating. Galaxies are moving apart faster and faster. Something we call dark energy is driving this acceleration. We don't know what dark energy is, but we can measure its effects on the expansion of space-time. We know time is relative. It runs at different rates depending on how fast you're moving and how deep you are in a gravitational field. Astronauts on the International Space Station age slightly slower than people on the ground. The difference is tiny, measured in microseconds over months in orbit. But it's real and measurable. Atomic clocks at different altitudes run at different rates. A clock in the mountains runs slightly faster than a clock at sea level, because the clock in the mountains is farther from Earth's center, experiencing slightly weaker gravity. These effects have been measured countless times. They're used in practical technology, like GPS. They're fundamental features of how space-time works. We know that very strong gravity can create exotic objects. Black holes exist. We've photographed their shadows. We've detected gravitational waves from black hole mergers. Neutron stars exist. Incredibly dense objects where a star's mass is compressed into a sphere about 12 miles across. The density is so extreme that a teaspoon of neutron star material would weigh billions of tons. We know singularities appear in the mathematics, points where curvature becomes infinite and the equations break down. At the center of black holes, at the Big Bang, these singularities tell us that general relativity is incomplete, that something else must take over in these extreme conditions. Some quantum theory of gravity that can handle infinite curvature without producing infinite answers. We know black holes emit Hawking radiation. At least, the theory predicts they do. We haven't directly observed this yet, because the radiation from astrophysical black holes is far too weak to detect. But the theoretical prediction is solid, coming from combining quantum mechanics with general relativity. We know entanglement is real. Quantum particles can be correlated across arbitrary distances. This has been verified in countless experiments. We know wormholes are solutions to Einstein's equations. They're mathematically allowed. Whether they exist in nature, whether they're stable, whether they could be traversed, these are open questions. We know general relativity is incomplete. It doesn't incorporate quantum mechanics. It predicts singularities where it breaks down. It needs to be extended, modified, or replaced by something deeper. We know quantum mechanics is also incomplete on its own. It treats space-time as a fixed background. It doesn't account for the fact that space-time itself is dynamic and can be curved. We need a theory that combines both. That's the quest for quantum gravity. And we're working on it. Thousands of physicists around the world are tackling this problem from different angles. Some are working on string theory, trying to extract testable predictions, trying to prove that smooth space-time emerges from the theory at large scales, trying to understand which of the many possible solutions describes our universe. Some are working on loop quantum gravity, trying to show how smooth space-time emerges from the quantum loops, trying to make predictions that can be tested, trying to incorporate all the forces of nature into the framework. Some are exploring holography and entanglement, trying to understand how space itself might emerge from quantum information, building toy models where this can be proven rigorously, working toward extending these ideas to realistic models of our universe. Some are working on black hole physics, trying to resolve the information paradox completely, trying to understand what happens at the singularity, using insights from quantum information theory and holography. Some are working on cosmology, trying to understand what happened at the Big Bang, whether there was a time before it, what set the initial conditions, why the early universe had such low entropy. Some are working on experimental tests, looking for signatures of quantum gravity in cosmological observations, in the cosmic microwave background, in gravitational waves, in high-energy particle collisions. The effects are expected to be tiny, but with increasingly sensitive instruments, we might be able to detect them. It's one of the great intellectual adventures of our time. This quest to understand what space-time really is, to develop a quantum theory of gravity, to answer these profound questions about the nature of reality, and eventually, someone will figure it out. Someone will have the insight that cracks the problem open. Someone will develop the mathematics that describes what space-time really is at the fundamental level. It might happen in the next decade. It might take a century or more. But it will happen, because that's what humans do. We ask questions. We don't accept mystery as the final answer. We keep pushing, Keep exploring. Keep trying to understand. When that breakthrough comes, when we finally understand space-time at the deepest level, it will change how we see reality. It might change what we think is possible. It will certainly answer questions that have puzzled us for generations. And it will probably raise new questions we haven't thought to ask yet, because that's how science works. Every answer opens new questions. Every mystery solved reveals deeper mysteries. But that's not discouraging. That's exciting. It means there's always more to discover, always new frontiers to explore, always deeper levels of understanding to achieve. We know the universe is expanding. Space-time itself is growing larger. Galaxies are moving apart, not because they're traveling through space, but because space itself is expanding between them. We know this expansion is accelerating. Some mysterious form of energy, called dark energy, is pushing space-time to expand faster and faster. About 70% of the energy in the universe is in this form. We don't know what it is, but we can measure its effects. We know the universe had a beginning. About 13.8 billion years ago, the universe was in an extremely hot, dense state. It's been expanding and cooling ever since. We can see the afterglow of that hot early state in the cosmic microwave background radiation that fills all of space. Let me tell you more about this, because it's one of the most remarkable discoveries in the history of science. In 1929, Edwin Hubble made an observation that changed everything. He was studying distant galaxies, measuring their distances and their velocities. He found that almost all galaxies are moving away from us, and the farther away they are, the faster they're receding. This wasn't because we're at the center of the universe. It's because space itself is expanding. Every point in space is moving away from every other point. Imagine baking a loaf of raisin bread. As the dough rises, the raisins move apart from each other, not because they're moving through the dough, but because the dough itself is expanding. From the perspective of any raisin, all the other raisins appear to be moving away. And the farther away another raisin is, the faster it appears to be receding. That's what's happening with galaxies in the universe. Space itself is expanding, carrying galaxies along with it. If space is expanding now, that means it was smaller in the past. Run the expansion backward in time, and you find that the universe was once much smaller and much denser. Keep going back, and you reach a point where the entire observable universe was compressed into a tiny, incredibly hot, incredibly dense state. This is the Big Bang. Not an explosion in space, but an expansion of space itself. The cosmic microwave background is light left over from that early hot state. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Before that, it was too hot. Any atoms that formed would immediately be torn apart by energetic photons. The universe was opaque, filled with a hot plasma of electrons and atomic nuclei. But when the temperature dropped below about 3,000 degrees Kelvin, electrons could finally combine with nuclei to form stable atoms. Suddenly, the universe became transparent. Photons that had been constantly scattering off free electrons could now travel freely through space. Those photons are still traveling through space today. They've been stretched by the expansion of the universe. What started as visible and infrared light has been redshifted into microwave wavelengths. This is the cosmic microwave background radiation. It fills all of space. No matter which direction you look, you see it. It's incredibly uniform. the same temperature in every direction to within 1 part in 100,000, about 2.7 degrees above absolute zero. But there are tiny variations, tiny differences in temperature from one part of the sky to another. These variations show us what the universe looked like when it was 380,000 years old. They're like a baby picture of the universe. And these tiny variations are important. They show us that the early universe wasn't perfectly smooth. There were regions that were slightly denser than average, and regions that were slightly less dense. Over billions of years, gravity amplified these tiny differences. Denser regions attracted more matter, becoming even denser. They collapsed under their own gravity, forming the first stars and galaxies. Less dense regions became cosmic voids, vast empty regions of space. The pattern of variations in the cosmic microwave background tells us about the conditions in the very early universe. By analyzing this pattern, cosmologists can determine the age of the universe, the rate of expansion, the total amount of matter and energy, and the relative proportions of ordinary matter, dark matter, and dark energy. This is how we know the universe is 13.8 billion years old. How we know that ordinary matter, the stuff that makes up stars and planets and you, is only about 5% of the total energy in the universe. Dark matter makes up about 27%. And dark energy makes up about 68%. Dark energy is particularly mysterious. It's causing the expansion of the universe to accelerate. Galaxies are moving apart faster and faster. This was discovered in 1998 when astronomers were studying distant supernovae. They expected to find that the expansion of the universe was slowing down due to gravity. Instead, they found it was speeding up. Something is pushing space to expand faster. We call it dark energy, but we don't know what it is. It might be a property of space itself, what Einstein called the cosmological constant. Or it might be some kind of field pervading all of space. We don't know. What we do know is that general relativity describes the expansion of the universe remarkably well. The equations predict that a universe filled with matter and energy will evolve dynamically. It will either expand or contract. It can't stay static. Einstein initially resisted this conclusion. When he first applied his equations to cosmology in 1917, he found they predicted an expanding or contracting universe. He thought this must be wrong. Everyone believed the universe was static, unchanging. So Einstein added a term to his equations, the cosmological constant, to make a static universe possible. He later called this his biggest blunder. Because in 1929, Hubble discovered that the universe is indeed expanding. Einstein's original equations, without the cosmological constant, had predicted this. The universe is not static. It's dynamic, evolving, expanding. And now we know that the cosmological constant, or something like it, is actually necessary, but not to make the universe static, to explain why the expansion is accelerating. The more we study the universe, the more we find that general relativity describes it accurately. The expansion, the formation of structure, the behavior of black holes, gravitational lensing, gravitational waves, all of it matches Einstein's predictions. But general relativity also tells us where it breaks down, where it can't be trusted. At the Big Bang, the equations predict a singularity, a point of infinite density and infinite curvature where the laws of physics, as we understand them, cease to work. General relativity is telling us that something else must take over. Some quantum theory of gravity that can describe what really happened at t=0. The same is true inside black holes. At the center of every black hole, general relativity predicts a singularity, a point where space-time curvature becomes infinite. But infinities in physics usually mean you're using the wrong theory. They're signs that your equations have reached their limit, that you need a deeper theory to go further. This is why physicists are so focused on quantum gravity, not just out of intellectual curiosity, though that's part of it, but because general relativity itself is telling us that it's incomplete, that there's something deeper we need to understand. We know general relativity breaks down at singularities, places like the Big Bang or the center of black holes, where curvature becomes infinite and the equations stop working. This tells us that general relativity is not the final answer. It's an approximation that works brilliantly in most situations, but fails at the most extreme conditions. We know quantum mechanics is also not the final answer on its own. It describes the behavior of particles and forces beautifully, but it treats space-time as a fixed background. It doesn't account for the fact that space-time itself is dynamic and can be curved. We need a theory that combines both, a quantum theory of gravity, and we're working on it. Thousands of physicists around the world are tackling this problem from different angles. Some are working on string theory, trying to extract testable predictions or prove that it really does reduce to general relativity at large scales. Some are working on loop quantum gravity, trying to show how smooth space-time emerges from the quantum structure. Some are exploring holography and entanglement, trying to understand how space itself might emerge from quantum information. It's one of the great intellectual adventures of our time, and eventually, someone will figure it out. Someone will have the insight that cracks the problem open. Someone will develop the mathematics that describes what space-time really is. When that happens, when we finally understand space-time at the deepest level, it will change how we see reality. It might change what we think is possible. It will certainly answer questions that have puzzled us for generations. So let's come back to where we started. Space-time. You've heard the word your whole life. You use it every day without thinking about it. Your GPS works because engineers understand how space-time behaves. But what is it really? What is it made of? Is it fundamental or emergent? Does it exist at the smallest scales, or does something else, something more fundamental, give rise to it? We don't know. And that's okay. That's where the adventure is. That's where science happens. Not in the answers we've already found, but in the questions we're still trying to answer. Not in the settled theories we learned in school, but in the mysteries at the boundary of knowledge. Einstein gave us the idea of space-time over 100 years ago. It revolutionized physics. It explained gravity in a completely new way. It predicted black holes and gravitational waves and the expansion of the universe. It's been one of the most successful theories in the history of science. But Einstein himself would probably be the first to admit that it's not the end of the story. It's not the final answer. It's a step along the way. A beautiful, elegant, powerful step, but still just a step. The final answer is waiting, somewhere in the mathematics, somewhere in the patterns of quantum entanglement, somewhere in the structure of strings or loops or whatever the fundamental building blocks turn out to be. And when we find it, when someone finally cracks the code and figures out what space-time really is, it will be one of the greatest moments in human history. The moment when we finally understood the fabric of reality itself. Until then, we keep working. We keep testing theories. We keep building more sensitive detectors to measure gravitational waves and observe black holes and probe the structure of spacetime. We keep developing new mathematics to describe possibilities we haven't imagined yet, because that's what humans do. We look at the universe, we wonder, we ask questions, and we don't stop until we find answers. So the next time you use your phone's GPS, or you see an image of a black hole, or you read about gravitational waves, remember this. You're looking at one of the deepest mysteries in all of science. You're seeing evidence of something we use but don't fully understand. An idea that works perfectly in practice but remains mysterious in principle. Space-time is real. We can measure it. We can photograph it. We can detect waves moving through it. But we don't know what it is. Not really. Not at the deepest level. And that's beautiful in its own way. It means there's still more to discover, still more to understand, still mysteries waiting to be solved. The universe is telling us that reality is stranger and more wonderful than we ever imagined. That space and time, the most basic aspects of existence, are themselves mysteries waiting to be unraveled. And somewhere, right now, someone might be working on the insight that will finally solve it. The next Einstein, the next Hawking. Someone who will show us what space-time really is. When that day comes, remember that you were here at the beginning. You were here when we admitted we didn't know, when we stood at the boundary of knowledge and looked out into the unknown. Thanks for joining me on this journey into one of the deepest mysteries in physics. If you found this exploration valuable, a like or subscribe really helps the channel continue making these deep dives into space and science. And remember, we live in a universe where space and time are woven together into something we call space-time. We can see it, measure it, use it, but we still don't fully understand it. And that's what makes it worth studying. Good night, and keep looking up at the stars.